Hello everyone! First of all, I would like to thank the organizers of this meeting for inviting me. It's just really wonderful to be here with all of you. I'm Bing-Xue, a PhD student from School of Life Sciences, Northwestern Polytechnical University, and Jian is my supervisor. The topic of my presentation is a multi-label graph learning framework, enhanced by pathway interdependence for metabolic pathway prediction. In my presentation, I will focus on 5 major sections: background, scientific issues, methods, experiments, and summary. Okay, let's start with the background. Drug metabolism prediction is a critical part of drug discovery. Almost all chemical reactions in drug metabolism are catalyzed by enzymes, and many enzymes act sequentially to form a multi-enzyme system. The reactions from A to E or A to G is a metabolic pathway. A is the initial reactant. B, C, D, and F is the intermediates. E and G is the final reactant. In the process of finding lead compounds, it is important to identify which metabolic pathways a compound attains, especially for optimizing drugs' metabolic stability, toxicity, and bioavailability. However, a compound would attain one or more pathways. Label L0 to L10 represent different types of metabolic pathways, such as carbohydrate metabolism, energy metabolism, etc. As we can see in the figure, drug A is metabolized by 5 pathway types: L0, L3, L5, L7, and L9. L7 appears in drug A and C. L0 appears in drug A, C, and D. L2, L8, and L10 only appear in drug B. As a compound has multiple metabolic pathway types, it is important to identify the metabolic pathway types the compound is involved in. Okay, let's go to the second part, scientific issues. Biological experiments are always costly and time-consuming to identify pathways among a set of pathway combinations. In recent years, computational methods, especially machine learning-based methods and deep learning-based methods, are promising to predict possible metabolic pathways rapidly. Former machine learning-based methods included network-based methods, classification-based methods, and random key label set methods. Usually, a compound can adopt a multi-label classification directly. Each compound is encoded by this method. For example, the first compound has 5 pathway types, and we can encode it by 1 in the corresponding location, and we can encode it by 0 in the rest. Network-based methods generally construct certain interaction networks and infer potential pathway types for compounds. Early methods constructed chemical-chemical interactions to predict 11 kinds of metabolic pathway types. As its extension, other methods proposed a heterogeneous network including chemicals, enzymes, chemical-chemical interactions, chemical-protein interactions, and protein-protein interactions information, where nodes are chemicals or enzymes, and edges are interactions between nodes. However, these methods provided the range of metabolic pathway types for a given compound. That is, they cannot determine which types were predictions. Classification-based methods use the technique of multi-label learning to infer potential metabolic pathways. The multi-label classification can be converted into 1 or more boundary classifications. Compound pathway pairs as new samples, where positive samples are initial labels, and negative samples are not labels. Another method constructed 12 pathway-specific boundary classifiers for each pathway type. In the meanwhile, they adopted SVM as classifiers. However, these methods aggregate the imbalance between positive and negative samples by generating many negative samples. Another method, random k-label set methods, treat each kind of label combinations as new label. It turns the multi-label classification into a multi-class classification. Compared to the previous boundary classification, it provides the co-occurrence of multiple labels. However, this method also faces the imbalance issue where new combined labels usually account for few samples. Recently, deep learning-based methods used multi-label classification directly and used GNN to extract features. For example, GCN-based model and GAT-based model used GCN and GAT respectively to extract compound features based on 2D compound graphs, and added them with features derived from fingerprints and molecular properties. Although existing methods have achieved inspiring performance in metabolic pathway prediction, they neglect the dependence between pathway types. Also, it is inadequate to interpret why a compound attains a specific metabolic pathway from existing computational methods. After investigating more papers, we ensure that there is a dependence between pathways, which is caused by asymmetric pathway crosstalk. For example, both carbohydrate metabolism and lipid metabolism are affected by the metabolism of cofactors and vitamins. The big group vitamins help convert carbohydrates into energy in carbohydrate metabolism. In addition, the lack of vitamin B1, vitamin B6, and B12 leads to a significant increment of lipid deposits in the aorta. Moreover, such a pathway interdependence is asymmetric relationships between pathways. Therefore, the degree of influence of A may not equal to B. We suppose that the features of asymmetric interdependencies among pathways would enhance the prediction when a compound participates in uncertain numbers of metabolic pathways. Okay, let's go to the third part. To address pathway interdependence and interpretability, we develop a multi-label graph learning framework enhanced by pathway interdependence for metabolic pathway prediction. This end-to-end framework contains a compound encoder, a pathway encoder, and a multi-label predictor. The compound encoder learns compound embedding representations based on molecular graphs, while the pathway encoder learns pathway interdependence embeddings. The multi-label prediction identifies which pathways a compound attains based on two kinds of embeddings. The compound encoder adopts a two-layer GNN architecture, learns compound embedding representations by using molecular graphs. Its first layer is a GAT, which captures the importance of chemical bonds to pathways. The second layer is a GCN, which filter extracts all-term features by aggregating neighboring all-term features, and is followed by a global polling layer to generate compound embeddings. The pathway encoder generates pathway embeddings by two-layer GCN on a pathway dependence graph. The construction of the graph includes two phases: node initialization and edge building. The node initialization assigns initial node features. Considering that pathway names are semantic, we apply GLAV, a word representation tool, to implement the pre-training. For the pathway set, GLAV generates initial pathway embeddings by learning word embeddings of semantic pathway names. The edge building contains four steps to capture the pathway interdependence. Firstly, We construct a co-occurrence matrix based on the number of co-occurrences of each metabolic pathway type on the training dataset. Then, we calculated the probability matrix based on the co-occurrence matrix. That is, when one metabolic pathway type occurs, the probability of another metabolic pathway type occurring. Thirdly, to address the possible long-tail distribution probability matrix, we turned the conditional probability matrix to a boundary matrix by a hard threshold. Lastly, to enhance the node distinguishability during the aggregation of neighboring nodes, an extra reweighting scheme is utilized. Once the pathway interdependence graph is constructed, two layers of GCN are used to learn pathway embeddings. The initial pathway feature matrix passed through a GCN layer and updated by the propagating rule, and alpha is a trade-off coefficient. After obtaining compound embeddings and pathway embeddings, we can directly identify the pathway set in which a compound could attend. However, such a direct measure would be senseless since the compound embedding space and the pathway embedding space are of different vector spaces. To address this issue, we design an adapter to map the compound embedding space into the pathway embedding space. Okay, let's go to the first part, experiments. The experimental dataset contains 11 types of metabolic pathways. Was taken from GCN-based model. The dataset contains over 6,000 compounds and over 11,000 metabolic pathway entries. Meanwhile, there are more than 700 compounds attend to metabolic pathway types, and 38 compounds attend 11 pathway types. We assessed the performance of our model by the comparisons with two state-of-the-art machine learning methods, including random forest and XGBoost, as well as two state-of-the-art deep learning methods, including a GCN-based model and a GAT-based model. We used tenfold cross-validation for all the methods and measured their performance by two groups of metrics. The general matrix contains the average accuracy, precision, recall, and FE score. The greater, the better. The multi-label matrix contains Hamming loss, coverage, Van error, and ranking loss, which are metrics for multi-label learning. The smaller, the better. The results show that our model achieves the best performance with significant improvements over all the metrics. In this section, we investigated the importance of each module in our model. We made 3 variants of our model, of which the first removes the pathway encoder, the second one lacks the adapter in the multi-label predictor. The third alerts the pre-trained node feature vectors in the pathway dependence graph to randomly initialized Gaussian vectors. In general, the pathway encoder, the adapter, and the pre-training method play indispensable roles in predicting multi-label metabolic pathways. After that, we explore the interpretability of our model. Our model uses the GAT layer in its compound encoder to assess why a compound participates in a specific pathway. Since the attention weights learned in the GAT layer can reflect the importance of chemical bonds in compounds, we can reverse the association between compound substructures and their metabolic pathway. For example, energy metabolism and amino acid metabolism are two important pathway types. The visualized attention weights show that the most carbon-based chemical bonds concentrating compound backbones usually have small attention values. More importantly, the visualization reveals that the crucial substructures having high attentions are pathway specific. In summary, our model is an interpretable model which can indicate compound substructures significantly associated with metabolic pathways. It would help reveal why a compound participates in a specific pathway. Okay, let's go to the final part, summary. In summary, the main contributions of our model are as follows. Firstly, it provides an interpretable manner to indicate crucial compound substructures which are significantly associated with metabolic pathways by molecular graph attention embedding. Secondly, by capturing the pathway interdependence, it significantly improves the characterization of the relevance between compounds and their metabolic pathways. Thirdly, it provides a direct multi-pathway prediction method by measuring the proximity between compounds and metabolic pathways in a common embedding space. Finally, we believe that our study provides new insights into label dependence representation learning for other multi-label classification problems, for example, drug toxicity prediction in drug discovery. Also, it is anticipated that interpretable techniques derived from image processing, for example, visualization of hidden layers, nearest neighbors, and GAN, can be used to achieve better interpretability in predicting metabolic pathways for compounds. Okay, thanks for listening and welcome questions.